Imagine that the world you see is only one layer of reality. Everything you touch, every decision you make, every moment you remember feels solid and permanent. It feels singular, as if this universe is the only stage on which existence unfolds. But what if that certainty is only an illusion of perception? What if reality is not a single timeline moving forward, but a vast structure of countless parallel existences unfolding at the same time? And what if, at this very moment, one of those realities is not just existing beside ours, but slowly interacting with it? For decades, the idea of parallel universes lived safely inside science fiction. It belonged to novels, films, and imagination. A fascinating possibility, but nothing more. Then, physics began to change. As scientists explored the deepest layers of matter and energy, the universe started behaving in ways that defied common sense. Particles existed in multiple states at once. Events refused to settle into a single outcome. Reality itself appeared unstable at its most fundamental level. The deeper we looked, the less solid existence became. Quantum mechanics revealed a universe where certainty dissolves into probability, where particles do not choose a single path until they are observed, where multiple outcomes can exist simultaneously, suspended in a strange and delicate balance. From this strange behavior emerged a radical idea. What if reality never chooses just one outcome? What if every possible result actually happens, but in separate branching universes? This concept became known as the many worlds interpretation. First proposed in 1957 by a young physicist named Hugh Everett, it suggested something extraordinary. The universe does not collapse into one version of events. Instead, it continuously divides. Every quantum event, every interaction, every choice, each one creates a new branch of reality. In one universe, a particle moves left. In another, it moves right. In one reality, a decision leads you down one path. In another, a different version of you walks another. According to this view, the cosmos is not a single unfolding story. It is an endless network of parallel narratives, all existing at once. For many years, this idea seemed too vast, too extravagant to accept. An infinity of unseen worlds felt unnecessary, almost philosophical rather than scientific. But the mathematics remained consistent, and as technology advanced, new discoveries began to hint that reality might be far stranger than anyone imagined. Quantum computers, machines that operate on the principles of superposition and entanglement, appeared capable of exploring multiple solutions simultaneously. Some physicists suggested that these devices were not merely calculating faster than classical machines. They might be performing computations across parallel realities. The implications were staggering. If true, it would mean that other universes are not just theoretical constructs. They are woven into the very fabric of our physics, influencing processes in ways we are only beginning to understand. Yet the story does not end with quantum theory. When scientists turned their instruments toward the vastness of space, they found something even more unsettling. A faint but unmistakable irregularity embedded in the oldest light of the universe. The cosmic microwave background is often described as the afterglow of the Big Bang. A faint radiation that fills all of space, preserving a snapshot of the universe when it was only a few 100,000 years old. It is one of the most precise maps humanity has ever created, and within that map lies a mystery, a region known as the cold spot, an enormous area of space significantly colder than surrounding regions, far larger than current cosmological models can easily explain. At first, scientists believed it might be caused by a massive empty region of space, a cosmic void stretching across hundreds of millions of light years. But deeper analysis revealed problems with that explanation. The cold spot was too large, too uniform, too statistically unlikely. It was as if something had disturbed the structure of the early universe itself. This anomaly opened the door to a possibility once considered almost unthinkable. What if that cold region is not simply an empty patch of space? What if it is the imprint of an interaction between our universe and another? Some cosmological models propose that our universe may exist like a vast membrane, floating within a higher dimensional space. If other universes exist as similar structures nearby, collisions or interactions could leave subtle scars in the cosmic background radiation. A faint bruise in the oldest light, a mark left by another reality brushing against our own. If such an event occurred, it would not resemble an explosion or a dramatic tear in space. The evidence would be quiet, statistical, hidden within patterns of radiation and probability. A whisper rather than a collision. And yet, even a whisper would change everything, because it would mean that our universe is not alone, not isolated, not self-contained. It would mean we are part of a far larger structure of existence, where multiple realities coexist and occasionally influence one another. As these ideas continue to develop, physicists have begun exploring even more unsettling possibilities. One theory suggests that alongside our universe, moving forward through time, there may exist a mirror universe moving in the opposite direction. A cosmic reflection where time flows backward and matter is balanced by antimatter. Together, both universes would form a perfectly symmetrical system, preserving fundamental physical laws across a larger cosmic framework. Another possibility suggests that what we perceive as dark matter, the invisible substance making up most of the universe's mass, could be evidence of particles originating from another reality. Particles that interact gravitationally with our world, yet remain otherwise hidden from direct detection. Each new hypothesis pushes the boundary of what we consider possible. Each new observation challenges the assumption that reality is simple and singular. The deeper we look, the more the universe resembles a vast, interconnected system rather than a single, isolated existence. All of this leads to a profound and unsettling question. If other realities exist, if they branch, collide, or mirror our own, then what does it truly mean to exist in this one? Are we living in just one version of countless possible worlds? Are there other versions of ourselves experiencing different outcomes at this very moment? And could the universe we inhabit be quietly interacting with realms we cannot see? These questions move beyond physics into philosophy, beyond observation into identity. They force us to reconsider what we mean by reality itself. For centuries, humanity believed the universe was stable and predictable, a vast but orderly system governed by clear laws. Now, the evidence suggests something far more complex, a cosmos where certainty dissolves into probability, where reality may branch endlessly, where unseen universes could exist alongside our own, separated by dimensions we cannot perceive, and perhaps, occasionally, touching. Over the course of this documentary, we will explore the scientific foundations behind these ideas. the experiments that led physicists to question the nature of reality, the anomalies that refuse to be explained, and the theories that attempt to describe a universe far more intricate than anything previously imagined. This is not a journey into fantasy, it is an exploration of the most advanced scientific thinking of our time. A journey to the edge of what is known and into the possibilities that lie beyond. Because if another universe is already colliding with ours, the signs will not appear as dramatic events in the sky. They will appear as subtle inconsistencies in data, small distortions in the structure of space, quiet clues hidden within the mathematics of reality. The universe rarely announces its deepest secrets loudly. More often, it reveals them in whispers. And if we listen carefully enough, we may discover that reality is far larger and far stranger than we ever imagined. Long before modern technology allowed us to observe the universe in extraordinary detail, humanity believed reality was simple. The cosmos was thought to be a single continuous story. One beginning, one timeline, one unfolding existence moving steadily forward through time. For centuries, this assumption remained largely unchallenged. The universe appeared stable, predictable, governed by laws that could be measured and understood. Then, in the early 20th century, physics encountered something deeply unsettling. As scientists began examining matter at extremely small scales, they discovered that the classical rules of reality no longer applied. Particles behaved in ways that contradicted everything previously understood about motion, position, and certainty. An electron, for example, could not be described as a simple object moving through space. Instead, it behaved like a cloud of possibilities. It could exist in multiple positions simultaneously, only appearing in a definite place when measured. This strange behavior became the foundation of quantum mechanics, a new branch of physics that described reality not as a set of fixed outcomes, but as a spectrum of probabilities. At first, even the greatest minds in science struggled to accept these findings. Albert Einstein himself resisted the idea that reality could be fundamentally uncertain. He famously objected to the randomness implied by quantum theory, insisting that the universe must obey deeper deterministic rules. Yet experiment after experiment confirmed the same conclusion. At the smallest scales, certainty dissolved into probability. Reality behaved less like a solid structure and more like a shifting field of potential outcomes. To explain this, physicists developed what became known as the Copenhagen interpretation. According to this view, quantum particles exist in a state of superposition, occupying multiple possibilities at once. Only when observed or measured does this superposition collapse into a single definite state. In simple terms, reality remains fluid until it is observed. This interpretation became widely accepted because it matched experimental results, but it came with a troubling implication. If observation causes reality to settle into one outcome, what exactly qualifies as an observer? Does consciousness play a role? Does reality only become definite when measured by a human mind? These questions created a philosophical tension within physics. The equations worked perfectly, yet their meaning remained deeply mysterious. For decades, most physicists accepted the Copenhagen interpretation as a practical solution, even if its deeper implications remained unresolved. The focus remained on predicting outcomes rather than questioning the underlying nature of reality. Then, in 1957, a young graduate student at Princeton University proposed a radically different perspective. His name was Hugh Everett III. Everett was not satisfied with the idea that reality simply collapses when observed. To him, the collapse of the wave function felt artificial, an added rule that existed only to make the mathematics align with human perception. Instead, he proposed something far more extraordinary. What if the wave function never collapses at all? What if every possible outcome of a quantum event actually occurs, but in separate, parallel branches of reality? According to Everett's interpretation, when a quantum measurement takes place, the universe does not choose a single result. Instead, it splits. In one branch, one outcome is observed. In another branch, a different outcome occurs. Both branches are equally real, yet they no longer interact with each other. This idea eliminated the need for a mysterious collapse mechanism. The mathematics of quantum mechanics could remain consistent and continuous. Reality would simply expand into multiple versions rather than narrowing to one. Everett called this the relative state formulation of quantum mechanics. Later, it became widely known as the many worlds interpretation. At the time, his proposal was met with confusion and resistance. The physics community was not prepared to accept the existence of countless parallel universes created by every quantum interaction. To many scientists, the idea felt excessive, unnecessary, almost philosophical rather than scientific. Even Everett's academic advisors struggled with the implications. While they recognized the mathematical consistency of his work, they worried about its radical interpretation. The dominant view in physics remained firmly rooted in the Copenhagen interpretation. Reality collapsed into one outcome when observed. That was the practical model used in laboratories and textbooks. Everett's theory, by contrast, suggested that the universe continuously branches into an unimaginable number of parallel realities. Every quantum event would create new versions of the universe, each containing different outcomes. It was a breathtaking idea, and for many, it felt impossible to accept. Disappointed by the lack of support, Everett eventually left academia. He pursued a career outside mainstream theoretical physics, while his revolutionary interpretation remained largely overlooked. Yet the idea did not disappear. Over the following decades, a small number of physicists began revisiting Everett's work. They recognized that the many worlds interpretation solved certain conceptual problems within quantum mechanics more elegantly than traditional approaches. It removed the need for wave function collapse. It treated the equations of quantum theory as universally valid, and it provided a consistent explanation for superposition without introducing special exceptions for observation. Gradually, interest in the theory began to grow. By the late 20th century, advances in quantum computing and theoretical physics brought renewed attention to Everett's proposal. Some researchers began suggesting that the immense computational power of quantum systems might only be fully explained if multiple parallel outcomes were actually occurring. If a quantum computer can evaluate many possibilities simultaneously, where does that parallel processing take place? Within a single universe, or across multiple branches of reality? While the question remains open, it illustrates how Everett's once rejected idea continues to influence modern physics. Today, the many worlds interpretation remains one of several competing explanations for the behavior of quantum systems. It is neither fully proven nor fully dismissed, but its implications are profound. If correct, It means that reality is not a single continuous thread. It is a vast and constantly branching structure. Every moment, every interaction, every quantum event contributing to an ever-expanding network of parallel universes. In one branch, a particle behaves one way. In another, it behaves differently. In one reality, certain events unfold. In another, alternative outcomes take shape. Each branch exists independently, evolving according to its own sequence of events. From within any single branch, the universe appears stable and singular. But from a broader perspective, reality may be far more expansive than our senses can perceive. This raises an extraordinary possibility. If countless parallel realities exist, separated only by the delicate mechanism of quantum decoherence, could there ever be circumstances where those separations become less absolute? Could interactions occur between branches, however subtle or rare? Most interpretations suggest such interactions would be nearly impossible. Once branches diverge, they evolve independently. The information connecting them becomes effectively inaccessible. Yet physics has surprised us before. And as we continue exploring the foundations of quantum theory, the boundary between what is impossible and what is merely improbable becomes increasingly difficult to define. The idea that reality may consist of countless parallel worlds is no longer confined to speculative fiction. It is a serious scientific hypothesis emerging from the very equations that describe our universe. Whether those worlds remain forever separate, or whether they may occasionally influence one another, is a question that leads us deeper into the mysteries of existence. And it is a question we have only just begun to explore. Hugh Everett did not set out to write science fiction. He wanted a clean mathematical account of quantum mechanics that did not rely on mysterious, poorly defined processes. He wanted the equations to hold everywhere, at all times, without an exception for observation or measurement. His proposal was simple in principle and enormous in consequence. The equations that govern quantum systems, he argued, never break. They never collapse. They always evolve deterministically. What we call a measurement is not a magical forcing of one outcome. It is the branching of the universal wave function into separate, non-communicating branches. Imagine, for a moment, a tree. At every fork, a new branch grows. Each branch carries a different set of outcomes. Each branch is a complete world in which those outcomes play out. In this view, Schrödinger's cat is not trapped in a paradox of being both alive and dead at once. Instead, the universe contains a branch where the cat is alive and another branch where the cat is dead. Both outcomes occur, each in its own world. This does not mean the branches are obvious to us. From our perspective, we experience only one chain of outcomes, our branch. We are unaware of the others because once branches form, they cease to interfere in any practical way. The reason for that practical isolation is decoherence. Decoherence is the physical process that prevents quantum interference from persisting at macroscopic scales. A quantum system may exist in a delicate superposition, but as it interacts with its environment, with air molecules, thermal radiation, stray photons, the coherent phase relationships that allow interference are rapidly scrambled. Think of a choir singing in perfect harmony. A single subtle noise can throw one voice off pitch. As more voices become uncoordinated, the harmony collapses into noise. In quantum terms, the environment is that noise. It takes the coherent superposition and disperses the information into countless degrees of freedom. The result is not a mysterious collapse, it is an effective separation of branches. The quantum correlations that allowed interference are spread so widely that recombining them becomes essentially impossible. Decoherence explains why macroscopic objects behave classically, why we do not see cats that are simultaneously alive and dead, why our experience is continuous and determinate, even if, at the microscopic level, the universe remains a sea of possibilities. Yet the deeper philosophical questions remain. If every quantum event spawns branches, then what is probability? If all outcomes happen somewhere, what does it mean to say an event was likely or unlikely? Physicists and philosophers have wrestled with this problem for decades. Some solutions appeal to subjective experience. They argue that probability reflects an observer's uncertainty about which branch they will find themselves in after a branching event. Others attempt to ground probability in the mathematical structure of the wave function itself. They argue that branches have different weights, and those weights determine how likely an observer is to experience a given outcome. This remains a contested and subtle issue, one that underscores the conceptual difficulty of applying ordinary probability to a branching cosmos. Meanwhile, advances in quantum technology have pushed these debates from thought experiments into laboratories. Quantum computers manipulate superpositions and entanglement to perform computations that are infeasible on classical machines. They do not merely speed up calculations, they operate in a regime where the logic of quantum mechanics is exploited directly. David Deutsch, one of the pioneers of quantum computation, argued that quantum computers provide indirect support for a many worlds view. In his perspective, a quantum computer performs its work by exploring many computational paths simultaneously. Each path can be thought of as occurring in a different branch, and the final result emerges from their collective interference. This is a controversial claim. Not all scientists accept it as evidence. Quantum computation can be framed within other interpretations of quantum mechanics as well. But the striking power of these devices has forced physicists to confront uncomfortable questions about what the mathematics is actually describing. Experimentally, physicists have tested quantum systems with exquisite control. They have created superpositions in ever larger systems. They have observed interference patterns that disappear as decoherence sets in. They have created entangled states across increasing distances. Each of these experiments demonstrates that quantum mechanics does not care about our classical intuitions. It operates with consistent precision, even when its implications feel alien. Consider the double-slit experiment. When individual particles pass through two slits, they create an interference pattern characteristic of waves. If we attempt to determine which slit a particle passed through, the interference pattern is destroyed. From the many worlds vantage point, the act of measurement correlates the particle with the measuring device and the observer, creating branches in which different slit outcomes are recorded. From the perspective of a single branch, it appears as if the particle chose one slit or the other. From the broader quantum state, all possibilities were present until that entanglement with the environment produced effective decoherence. These insights do not simply reshape our metaphysical landscape. They have practical consequences. In quantum information theory, for instance, the fragility of coherence is a central challenge. Building a quantum computer requires protecting quantum states from decoherence long enough to perform useful operations. This technical problem has driven intense research into error correction, isolation, and clever engineering. But beyond the laboratories and equations lie human concerns. If there exist countless versions of ourselves, living out all possible variations of our choices, how do we interpret moral responsibility? Does the multiplication of outcomes dilute the significance of any individual action? For most practical purposes, it does not. Our subjective experience remains confined to one branch, and within that branch our choices have real consequences. The existence of other branches does not absolve us from responsibility in this one. Instead, the many worlds view invites a different kind of humility. It suggests that the cosmos may be far richer and more intricate than our everyday intuitions allow. It asks us to hold two truths at once: that our experience is singular and meaningful, and that it may be embedded within a vastly larger multiverse. The many worlds interpretation, whether ultimately true or not, forces us to reconsider the scope of scientific explanation. It pushes us to reconcile the precise deterministic equations of quantum mechanics with our lived experience of probability and choice. And it leaves open a tantalizing possibility. If branches are for the most part separate, then interactions between them must be extraordinarily rare. But the universe has surprised us before. It has a way of revealing the unexpected in the quiet corners of data and observation. Could there be conditions under which branches leave detectable traces on one another? Could the brush of a neighboring world leave a tiny imprint on our cosmological record? These are the questions that propel physicists and cosmologists forward, from the lab to the sky, from thought to measurement. Our next segment will examine how the physics of branching reaches outward into the cosmos, and how anomalies in the oldest light of the universe may hint at interactions far beyond the intuitive boundaries of our reality. Far beyond the laboratories of Earth, the universe itself preserves a record of its earliest moments. Long before stars formed, before galaxies took shape, before planets and life emerged, the cosmos existed as an extremely hot, dense sea of radiation and particles. As it expanded and cooled, that radiation stretched into longer wavelengths, eventually becoming what we now call the cosmic microwave background. This faint glow fills all of space. It is not visible to the human eye, yet with sensitive instruments it appears as a nearly uniform field of microwave radiation, bathing the universe in a quiet afterglow from its earliest epoch. To cosmologists, this radiation is a snapshot of the universe when it was only about 380,000 years old. It is one of the most valuable sources of information we possess about the origin and structure of everything. When scientists first mapped this radiation in detail, they expected to find a pattern that was nearly uniform. And for the most part, they did. The cosmic microwave background is remarkably consistent in temperature across the sky. Tiny fluctuations exist, but they are extremely small, representing minute differences in density that eventually led to the formation of galaxies and large-scale structures. Yet within this otherwise uniform field, researchers noticed something strange: a region of space that was significantly colder than its surroundings. Not by a large margin in absolute terms, but by enough to stand out clearly against statistical expectations. This region became known as the cold spot. At first, scientists assumed the anomaly could be explained by conventional means. Perhaps a vast cosmic void existed in that direction, an enormous region of space containing far fewer galaxies than average. Light passing through such a void could lose energy in a way that would make the background radiation appear slightly cooler. This explanation seemed reasonable. The universe contains structures of immense scale, and voids spanning hundreds of millions of light years are not unheard of. However, as observational data improved, doubts began to emerge. The cold spot appeared larger and more uniform than expected for a simple void. The statistical likelihood of such a feature arising purely from known cosmic structures seemed unusually low. It did not fit comfortably within the standard cosmological model. Researchers analyzed data from multiple satellites and surveys. They compared measurements from different instruments. They constructed simulations to determine how often such a feature should appear by chance. The results remained inconclusive but intriguing. The cold spot persisted. It refused to disappear under closer scrutiny. This raised an unsettling possibility. What if the anomaly was not caused by ordinary cosmic structures? What if it represented evidence of something far more unusual? One hypothesis suggested that the cold spot could be the imprint of a collision between our universe and another. Not a violent impact in the traditional sense, but a subtle interaction between large-scale cosmic structures existing in a higher dimensional framework. Some cosmological theories propose that our universe may be a kind of membrane embedded within a larger multi-dimensional space. Other universes, if they exist, might occupy nearby regions within that space. If two such structures came into contact during the early stages of cosmic evolution, the interaction could leave a detectable signature. That signature, according to some models, might appear as an anomalous region in the cosmic microwave background. A circular area where temperature fluctuations differ slightly from what standard models predict. Such a mark would be faint, statistical, difficult to distinguish from random fluctuations. But with enough precision, it might stand out as something real. The idea remains controversial. Many scientists caution that extraordinary claims require extraordinary evidence. The cold spot may yet find a conventional explanation as observational techniques continue to improve. But the mere existence of such an anomaly invites deeper investigation. It challenges the assumption that the observable universe is a closed system unaffected by anything beyond its boundaries. If our universe did experience a collision or interaction with another during its infancy, the consequences would be profound. It would suggest that our cosmos is not an isolated entity, but part of a larger structure of realities. To understand this possibility, researchers have explored models of cosmic inflation and higher dimensional cosmology. Some of these models describe the early universe as a rapidly expanding bubble within a larger multiverse. Other bubbles could form nearby, each representing a separate universe with its own physical properties. If two such bubbles expanded close enough to one another, their boundaries might meet. The interaction would not necessarily destroy either universe. Instead, it could produce subtle distortions in the distribution of energy and radiation. These distortions might persist for billions of years, visible today only as slight irregularities in the cosmic background radiation. Searching for such signatures has become an active area of research. Scientists analyze sky maps for circular patterns, unusual temperature distributions, and statistical anomalies that cannot be easily explained by known processes. So far, no definitive proof of a cosmic collision has been confirmed, but neither has the possibility been completely ruled out. The cold spot remains one of the most intriguing features in modern cosmology. It stands as a reminder that the universe still holds mysteries at scales far beyond everyday comprehension. If it is indeed the result of an interaction with another reality, then it represents the first observable hint that our universe is part of something larger. A vast structure in which multiple cosmic domains coexist and occasionally influence one another. Even if the anomaly eventually finds a conventional explanation, the search itself has expanded our understanding of what might be possible. It has pushed scientists to consider models of reality that extend beyond a single universe. As observations grow more precise and data accumulates, we move closer to answering a question that once belonged purely to speculation. Is our universe alone? Or does it exist within a broader multiverse where other realities form, evolve, and perhaps, on rare occasions, leave faint imprints upon our own? The answer may be written in the oldest light of the cosmos, in subtle patterns across the sky, in anomalies that refuse to conform to expectation. And as we continue to study those patterns, we edge closer to understanding whether the boundaries of our universe are as absolute as they seem, or whether they are far more permeable than we ever imagined. As cosmologists studied the large-scale structure of the universe and physicists examined the smallest particles of matter, another strange possibility began to emerge. A possibility that does not simply suggest multiple universes existing beside ours, but one that may be fundamentally linked to our own. A mirror universe. Not a duplicate in the ordinary sense. Not merely another version of reality branching from our decisions, but a cosmic twin born from the same origin, governed by the same laws, yet moving in the opposite direction through time. To understand this idea, we must begin with one of the most fundamental principles in physics, a principle known as symmetry. Symmetry governs the behavior of the physical world at its deepest level. If you rotate certain systems, the laws remain unchanged. If you shift them in space, the equations still apply. These invariances reveal underlying consistencies in the structure of reality. Among the most important symmetries in modern physics is something called CPT symmetry. The letters stand for charge, parity, and time. Together, they describe a transformation that should leave the fundamental laws of physics unchanged. Charge refers to switching particles with their oppositely charged counterparts. An electron becomes a positron. Matter becomes antimatter. Parity refers to flipping spatial coordinates as if the universe were reflected in a mirror. Left becomes right. Right becomes left. Time refers to reversing the direction in which events unfold. Instead of moving from past to future, processes run backward. Individually, these symmetries can be violated under certain conditions. Some particle interactions do not behave the same under mirror reflection or charge reversal. But when all three transformations are applied together, the combined symmetry appears to hold. This principle suggests that the fundamental equations describing the universe should remain consistent if charge, spatial orientation, and time are all reversed simultaneously. From this insight, some physicists proposed a remarkable idea. Perhaps the universe as a whole obeys CPT symmetry not within a single timeline, but across a pair of universes. In this model, the Big Bang did not create only one expanding cosmos, it created two. Our universe moves forward through time, expanding from the moment of its origin. A mirror universe moves in the opposite temporal direction, expanding away from the same origin but in reverse. From our perspective, time flows forward. From the perspective of the mirror universe, their time flows forward as well, but in the opposite direction relative to ours. Both universes together form a perfectly symmetrical system. Matter dominates in our universe. Antimatter dominates in the mirror universe. Together, the balance is preserved. This idea offers a potential explanation for one of the greatest puzzles in cosmology: the apparent imbalance between matter and antimatter. According to standard models, the Big Bang should have produced equal amounts of both. Yet our universe contains overwhelmingly more matter than antimatter. Where did the antimatter go? The mirror universe hypothesis suggests it did not disappear. It exists on the opposite side of the cosmic timeline, forming a complementary reality that restores symmetry across the whole system. In this framework, the Big Bang becomes a point of bifurcation, a moment where two universes emerge, each moving away from that origin in opposite temporal directions. From within either universe, time appears to move normally. Observers perceive a past and a future. Entropy appears to increase. Stars form, evolve, and eventually fade. But from a broader perspective, the two universes together form a balanced structure, obeying CPT symmetry across their combined existence. This concept has profound implications. If a mirror universe exists, it may contain particles that interact weakly with our own. Some theorists propose that what we perceive as dark matter could be evidence of such interactions. Dark matter exerts gravitational influence on galaxies and cosmic structures, yet it does not interact with light. It remains invisible, detectable only through its gravitational effects. If mirror universe particles exist and interact primarily through gravity, they could account for some or all of the dark matter observed in our universe. This remains speculative, but it illustrates how mirror universe theories attempt to address unresolved questions in cosmology. The idea of reversed time also challenges our intuitive understanding of causality. In everyday experience, causes precede effects. Events move from past to future in a linear progression. In a mirror universe moving in the opposite temporal direction, the sequence of cause and effect would appear reversed from our perspective. Processes that we perceive as increasing disorder would appear to move toward greater order, yet for observers within that universe, their experience of time would feel entirely normal. They would perceive themselves as moving forward, just as we do. This symmetry suggests that time's arrow may not be an absolute feature of reality, but a local property of our particular universe. The mirror universe hypothesis remains one of several attempts to understand the deep symmetries underlying physical law. It is not widely accepted as proven, but it has gained attention because of its elegant mathematical consistency and its potential to resolve certain cosmological puzzles. Whether such a universe truly exists is still unknown. Detecting it directly will be extraordinarily difficult. Any interaction between the two realities would likely be subtle, mediated primarily through gravitational effects. Yet the possibility itself expands our understanding of what reality might encompass. If our universe has a mirror counterpart, then existence is not a single, isolated timeline. It is part of a larger symmetrical structure extending beyond our direct perception. Combined with theories of parallel worlds and cosmic collisions, the mirror universe concept suggests that reality may be far more interconnected than we once believed. Not a solitary cosmos drifting in emptiness, but one component of a vast and intricate system of realities. Some separated by quantum branching, some by higher dimensional space, some perhaps by the direction of time itself. As we continue exploring these ideas, one theme becomes increasingly clear. The deeper we investigate the universe, the less it resembles a simple, self-contained structure. Instead, it appears as part of a far larger and more complex framework, one that may include multiple layers of existence interacting in ways we are only beginning to imagine. In the next part of this journey, we move beyond theoretical models and into the philosophical implications of these discoveries. Because if reality is indeed composed of multiple interconnected universes, the question is no longer only scientific, it becomes personal. If reality is larger than a single universe, then existence is not as simple as we once believed. For most of human history, people imagined themselves living within one continuous world, one life, one timeline, one irreversible sequence of events stretching from birth to death. Every choice felt permanent. Every lost opportunity felt final. Every decision seemed to close one path while opening another. But if modern physics is even partially correct, that certainty begins to dissolve. In a universe shaped by quantum branching, countless variations of events may unfold simultaneously. Each possibility realized somewhere within a vast network of parallel realities. In one version of existence, a decision leads to one outcome. In another, the same moment unfolds differently. Entire lifetimes diverge based on the smallest fluctuations. This idea challenges the very foundation of how we understand identity. If multiple versions of you exist, each experiencing different circumstances, then what defines the real you? Is it the version reading these words now, or the countless other versions living out alternate paths in parallel realities? From within our own experience, the answer feels obvious. We inhabit one continuous stream of consciousness, one narrative that feels singular and personal, yet the possibility of parallel selves raises unsettling questions. Not because it diminishes the importance of our experiences, but because it expands the scope of existence beyond our immediate perception. It suggests that individuality may be both unique and multiplied, that our personal story is deeply meaningful within our own branch of reality, while also being one of many variations unfolding across a vast multiverse. This does not make our choices irrelevant. Within the reality we inhabit, every decision still carries consequences. Every action shapes the world we experience. Every relationship, every success, every failure remains real and significant. But it does introduce a different perspective on possibility. If reality branches, then every potential outcome exists somewhere. Every path taken or not taken becomes part of a larger structure of existence. Every moment becomes a point of divergence within an expanding web of realities. Some people find this idea comforting. It suggests that no opportunity is ever truly lost, only realized in another version of events. Others find it unsettling, because it implies a loss of absolute uniqueness. Yet both reactions stem from the same realization. reality may be far more expansive than our senses reveal. The philosophical implications extend beyond personal identity. They reach into questions of free will and determinism. If every possible outcome occurs, does choice still matter? Or is the universe simply unfolding every possibility simultaneously? One perspective suggests that free will remains meaningful because our experience is confined to a single branch. Within that branch, our decisions shape the future we perceive. We do not experience the other outcomes directly, so our choices retain their significance. Another perspective views branching as a form of cosmic determinism. Every possibility unfolds somewhere, regardless of individual intention. From this viewpoint, reality becomes an immense structure of outcomes, each realized without preference. Neither interpretation has been conclusively proven. Both reflect attempts to reconcile human experience with the implications of modern physics. What remains clear is that the universe no longer appears as simple or singular as it once did. Beyond questions of identity and free will lies a deeper philosophical shift, a shift in how we perceive existence itself. For centuries, humanity placed itself at the center of a stable cosmos, a universe created once, unfolding in a predictable manner, a single stage upon which all events occur. Modern physics has gradually dismantled that certainty. It has revealed a cosmos where observation affects outcomes, where uncertainty is fundamental, where space and time themselves may be components of a larger structure. In this emerging picture, reality resembles an intricate tapestry rather than a single thread. Multiple layers of existence may coexist, some branching through quantum processes, some separated by dimensions beyond direct perception, some perhaps moving through time in directions we cannot easily comprehend. This does not reduce the meaning of our lives. If anything, it deepens it. To exist at all within such a vast and complex structure is extraordinary. To be conscious within a universe capable of generating countless realities is itself remarkable. Our experiences remain real within the context we inhabit. Our relationships, our memories, our ambitions retain their importance. The possibility of other realities does not erase the significance of this one. Instead, it invites a broader sense of wonder. It suggests that existence may be far richer than a single narrative, that the universe may be continuously exploring every possible variation of events. That reality itself may be an ever-expanding structure of possibilities unfolding across dimensions we are only beginning to understand. This perspective does not demand belief. It invites curiosity. It encourages us to examine the evidence, to consider the theories, and to remain open to the possibility that the universe is more intricate than our current models can fully capture. As science advances, the boundary between speculation and evidence continues to shift. Ideas once considered impossible become testable. Concepts once confined to imagination become subjects of serious research. The notion of multiple realities is no longer confined to fiction. It has entered the realm of scientific inquiry, supported by mathematical models and experimental observations that challenge traditional assumptions. Whether these theories ultimately prove correct remains uncertain. But their existence reflects a deeper truth. The universe is not obligated to conform to human expectations. It does not simplify itself for our comfort. It reveals its structure gradually, often in ways that challenge our most fundamental beliefs. If reality does extend beyond a single universe, if parallel worlds, mirror timelines, or higher dimensional interactions exist, then we are participants in a cosmos far more vast than we once imagined. And that realization carries a profound sense of both humility and awe. Because to understand the universe is not only to study distant stars and abstract equations, it is also to confront the nature of our own existence within that vast and mysterious whole. For thousands of years, humanity has searched for its place in the universe. We built stories to explain the stars. We developed mathematics to describe motion. We created instruments capable of observing galaxies billions of light years away. With each discovery, our understanding of reality expanded, and with each expansion came a deeper awareness of how little we truly know. Once, we believed Earth was the center of everything. Then, we discovered we orbit a single star among hundreds of billions within our galaxy. Later, we realized our galaxy is only one among trillions scattered across an immense cosmic web. Every step revealed a universe larger than previously imagined. Now, modern physics presents another possibility, that our entire universe may be only one component of a far greater structure, one reality among many. This idea does not arise from fantasy or speculation alone. It emerges from equations that describe quantum behavior with extraordinary accuracy, from observations of cosmic anomalies that resist simple explanation, from theoretical models that extend the known laws of physics beyond familiar boundaries. Each line of evidence remains incomplete. Each theory remains under investigation. But together, they form a pattern pointing toward a universe more complex than a single continuous reality. If multiple universes exist, they may take many forms. Some could branch continuously from quantum events, forming countless parallel versions of existence. Some might exist as separate cosmic domains within a larger multiverse. Some could mirror our own, balancing fundamental symmetries across time and matter. Others might interact only through gravity or subtle distortions in space-time. The details remain uncertain. The implications, however, are profound. If our universe is not alone, then existence itself is far more expansive than any single narrative can capture. Reality becomes a vast landscape of possibilities rather than a solitary path. This realization changes how we think about beginnings and endings, about chance and inevitability, about identity and meaning. It suggests that the story of existence is not confined to one timeline or one outcome. Instead, it may unfold across an immense network of realities, each exploring different variations of possibility. For some, this idea is unsettling. It challenges long-held assumptions about uniqueness and permanence. It raises questions about whether our experiences are singular or part of a broader pattern. For others, it is inspiring. It expands the horizon of what may be possible. It invites us to view existence as part of a vast and interconnected whole. Science does not yet provide definitive answers. The existence of other universes remains unconfirmed. The anomalies we observe may eventually find conventional explanations. The theories we explore may evolve or be replaced by new models. But the search itself continues to reshape our understanding. Every experiment probing the quantum realm, every telescope mapping the distant cosmos, every equation describing the structure of reality, all contribute to a deeper exploration of what existence truly is. Perhaps the most remarkable aspect of this journey is not the possibility of other universes, but the human capacity to imagine and investigate them. We are beings capable of asking questions that extend far beyond immediate experience, capable of constructing theories that reach to the edge of the observable universe and beyond, capable of confronting mysteries that challenge the limits of comprehension. Whether the multiverse proves real or remains theoretical, the process of exploring these ideas expands our perspective. It reminds us that knowledge is not static. It evolves with observation, with experimentation, with the willingness to question what once seemed certain. If another universe is already colliding with ours, the evidence will emerge gradually, not as dramatic events visible to the naked eye, but as subtle patterns hidden within data, as anomalies that persist despite careful analysis, as discoveries that force us to reconsider the boundaries of reality. And if no such collision exists, the search will still deepen our understanding of the cosmos we inhabit. It will refine our models, sharpen our instruments, and expand the reach of human curiosity. Either way, the journey continues. Because the universe, whatever its true structure may be, is vast beyond imagination. It invites exploration. It rewards curiosity. It challenges certainty. As we look toward the future, new generations of scientists will build more sensitive detectors, more powerful telescopes, more advanced quantum technologies. They will probe deeper into the nature of reality than ever before. Somewhere within that exploration may lie answers to questions that once seemed impossible to address. Answers about the origin of existence, about the structure of time and space, about whether our universe is singular or part of a greater whole. Until then, we stand at the threshold of understanding, aware that reality may extend far beyond what we perceive, aware that the universe still holds mysteries waiting to be uncovered, aware that every discovery brings us closer to understanding not only the cosmos, but our place within it. The search for truth does not end with certainty. It begins with curiosity. And as long as we continue to ask questions, to observe, to imagine, and to explore, the universe will continue to reveal its secrets, one discovery at a time. Perhaps, somewhere beyond the limits of our perception, other realities already exist. Perhaps they unfold quietly alongside our own, separated by dimensions we cannot yet reach. Perhaps they will forever remain beyond direct observation. Or perhaps, one day, we will find undeniable evidence that our universe is only one chapter in a far larger cosmic story. Until that moment arrives, we continue to look outward, to measure, to question, to wonder. Because in the vast silence of space and in the strange mathematics of quantum reality, there may already be signs that we are not alone in existence, not alone in the cosmos, not alone in reality itself. For most of human history, reality felt stable, solid, continuous, predictable. We believed the universe moved forward in a single direction, one timeline, one unfolding story. But the deeper we looked into the fabric of existence, the more that certainty began to dissolve. Quantum physics revealed that particles can exist in multiple states at once. Cosmology revealed anomalies in the oldest light of the universe. Mathematics revealed that reality may branch endlessly into parallel possibilities. Each discovery quietly challenged the assumption that we inhabit a single, isolated world. Now consider a possibility that is both simple and deeply unsettling. What if another universe is not just out there somewhere in the vast distance of space? What if it is already here? Not visible, not dramatic, not something that announces itself with explosions or distortions in the sky, but something subtle, something statistical, something hidden inside the structure of reality itself. If universes can exist side by side, if reality can branch into parallel timelines, if cosmic domains can form within a greater multiverse, then interaction between them may not be impossible. It may simply be difficult to detect. Imagine two realities existing extremely close together, separated by dimensions we cannot perceive. They would not collide like physical objects. They would overlap in ways that leave only faint traces. A slight irregularity in cosmic radiation, a statistical anomaly in physical measurements, a pattern that does not quite fit existing models. From our perspective, these would appear as unsolved mysteries, small inconsistencies in an otherwise predictable universe. But from a broader perspective, they might represent something far more profound. Evidence that our reality is not alone. Evidence that it is part of a larger structure of coexisting worlds. Now consider something even more unsettling. If multiple realities exist, and if branching occurs continuously at the quantum level, then countless versions of events may already be unfolding. Versions where different decisions were made. Versions where different histories occurred. Versions where outcomes diverged in ways we cannot perceive from within our own branch. Most of these realities would remain forever separate, isolated by the mechanism of decoherence. But if even the smallest interaction were possible, if even the faintest influence could pass between them, the consequences would be extraordinary. It would mean that reality is not fixed, not singular, not completely sealed. It would mean that what we experience as stable existence is only one layer within a far more complex structure. A structure where universes may form, evolve, and perhaps even influence one another across boundaries we do not yet understand. Some physicists believe that if such interactions occur, they would be subtle beyond comprehension. Not dramatic enough to disrupt daily life, not obvious enough to confirm easily. Instead, they would appear as anomalies, as patterns that refuse to conform to expectation, as quiet inconsistencies in the behavior of the cosmos. We may have already observed such signs without recognizing them for what they are. A region of space slightly colder than it should be. A quantum outcome slightly more probable than predicted. A measurement that resists perfect explanation. Individually, these details seem small, but together, they hint at a possibility that cannot be entirely dismissed. That reality itself may be more fluid than it appears. If another universe were already interacting with ours, we might not notice a dramatic shift. There would be no sudden transformation of the sky, no visible fracture in space. Instead, the change would be gradual, subtle, hidden within the mathematics of physical law. We would continue living our lives, unaware that the structure of reality might be far more complex than our senses reveal. And perhaps that is the most unsettling thought of all. Not that other universes exist somewhere beyond reach, but that they may exist alongside us, quietly influencing the fabric of existence in ways we cannot easily detect. It raises a final question. If reality can branch, merge, or coexist with other versions of itself, how would we know if something had already changed? If two timelines intersected, would there be a clear boundary between what was and what is? Or would the transition be seamless, leaving no obvious trace? Would memory remain consistent? Would history appear unchanged? Would the laws of physics continue operating as if nothing unusual had occurred? Or would we notice small inconsistencies, moments that feel slightly out of place, events that seem improbable yet real? It is possible that such questions will remain purely theoretical, that the universe is vast but ultimately isolated, that parallel realities, if they exist, never interact in measurable ways. But it is also possible that the truth is more complex, that reality is not a single, closed system, that it is part of a much larger structure of existence, that the boundaries between universes may not be as absolute as we once believed. As science advances, new instruments will probe deeper into space and deeper into the quantum realm. New data will challenge old assumptions. New discoveries will reshape our understanding of what is possible. Perhaps one day we will find definitive evidence of other realities. Or perhaps the clues are already present, hidden within patterns we have yet to fully understand. Until then, one possibility remains. You are experiencing one version of reality, one timeline, one sequence of events. But if the multiverse is real, if parallel worlds exist, if universes can coexist or interact, then somewhere, in ways beyond perception, other versions of reality may already be unfolding, and the universe you believe to be singular may be only one layer of something far greater, something vast, something complex, something that may already be closer than we think. Because if another universe is already colliding with ours, we might not be witnessing the beginning of that event. We might be living in the middle of it.